And welcome back. Or welcome. So, we want to we want to solve systems. And in our last video, we talked about how to solve them graphically. But in this video, we want to solve them without a graph. So, number one, reasons why we would want to solve it without a graph would be one, we don't want to do a whole bunch of extra effort to graph them just to find a solution that we can find easier. Number two, we want to flex those algebra skills. Number three, sometimes it's just, again, a lot easier and more exact. That's the real thing. You might notice from the original video that when we went to graph different things, now in this case it's nonlinear equations that we did, but notice when they stack on top of each other, they might not be directly on grid lines. It might look like this and then like that, and you've got this thing that you're not 100% sure. And if you want an exact solution, you can't really rely on a graph every time to be able to get an exact solution. So the only way to get exact solutions is to solve it algebraically. And let's just remember what a solution is. In this case, when we have two variables, a solution is an x and a y value, an ordered pair, that satisfies both of these equations. So it should be an ordered pair that, of some x, some y, that you can plug into both of these, and it will make both of the equations true. Because a solution is a set of values for your variables that make your equations true. So let's look at each one of these individually. I notice that I have y is equal to 2x plus 4. And I have y is equal to 4x minus 10. What's interesting here is that we know that if we want to satisfy both of these equations at the same time, that at this point where that solves them both our x and our x's should be the exact same value, and both of our y values should be the exact same value. So notice, this y is the exact same y that's in this, if they are to be solved at the same time, which means that we can either think of it as setting these two equal, since they're both equal to y. We can set them equal, which the property that we would be using in that case would be the transitive property. The transitive property is if A is equal to B and B is equal to C, then A is equal to C. So if Y is equal to this and this is equal to this, then this should be equal to this. It's called the transitive property. It's a fancy word. But you can also, usually the transitive property can also be written as a substitution property. We have a y here, and it's the same y here, which means that we can take this whole side of this equation and put it right there. We can take this and put it over here. So let's try it. Let's see what happens when we do that. Let's kind of get rid of this extra stuff because it was just an aside. So we can say that we have our 2x plus 4, and I'll keep them color-coded. Keep them color-coded. I apologize for that joke, especially since most of y'all won't get it. Your parents will. So we have, I kind of color-coded it a little bit. Maybe I changed the color of my equal sign. It doesn't really matter. But this would be true because both of our y's are the exact same y in the long run. Now, what we did by doing it like this is we got rid of y. I mean, it's still there in spirit, but we've gotten rid of it for this case. We've made a single equation with one variable, which is much easier to solve. You're going to find out that as systems get more and more variables, our job is always going to be to reduce it to an easier to solve system, and then reduce that until we have a single variable equation, because that's all we really know how to solve it at the end of the day. So let's go ahead and try to solve this equation like we would normally do. It's good review. So I want to solve for x. I either want I like x on my left side or my right side. It doesn't matter, but I want it on one side. It's on both sides right now, and I don't like that. So I want to get rid of it. So I'm going to do it two different ways. I'm going to do it one way, get through and find my x and my y value. But I'm going to do it a separate way as well, just to show you that it doesn't matter what side your x is on. So me, personally, I notice I have more x's on the right side. So to avoid having to do a bunch of fixing negatives, I'm going to try to get my x's on my right side and everything else on the other side. So let's go ahead and, I don't want this 2x on my left side if that's my goal. So I'll subtract 2x from both sides. Doing that, I have 2x minus 2x is 0. And I still have this plus 4 left. Now you might say, Mr. X, why are you writing the 0? Oh, you're right. I shouldn't. I don't need to. 2x minus 2x is 0, so they cancel additively, so we don't need to write it. My equal sign is still there. On the right side, I have 4x minus 2x is 2x, and I have my minus 10 just hanging out. So that's one thing, and then I can add 10 to both sides. So let's go ahead and add 10 to both sides. And on the left side, I get 14. On the right side, I get 2x minus 10 plus 10, so these two cancel out. So I can write it as 2x plus 0. Mr. X, stop writing the plus 0. You're right. I don't know what I was thinking. And the reason that I did that, the reason that I always do that, and the reason I subtracted 2x from both sides is because I wanted to get rid of a 2x on my left side, and the only way to do that is to subtract 2x from both sides. Number one, I have to do the same thing to both sides to maintain my equality. Number two, I always want to undo what was already there. So if I had a positive 2x and I wanted to get rid of it, I had to subtract 2x. If I had instead had a negative 2x on the left side and I wanted to get rid of it, I would have had to add. Whatever you need to do, but don't try to make magic happen. Make sure that you read it and say, all right, when I combine my like terms, I have 2x's minus 2x's, 0x's. And that's what you want to kind of say in that voice too, and send me a video of it or a Flipgrid so I can giggle. So in this case, I have a 2 times an x on my right side, and I just want x. So to get rid of it, I'm going to divide by 2 on both sides. I'm going to do the opposite operation. I was multiplying 2 onto my x, and I wanted to get rid of it, so I had to divide by 2. You can also think of it as multiplying by 1/2. And either way works, just depending on what is more efficient for the moment. But notice one thing. I did not divide by 2x. If I had done that, number one, I would have artificially destroyed a solution. Number two, I would have just gotten 1, and I wouldn't have known how to solve it after that. I would have gotten an equation that doesn't make sense. So I'm going to cancel my 2's because 2 divided by 2 is 1, so it cancels. It's a multiplicative identity. So multiplying by 1 didn't do anything, but that's why cancellation happens. And on the left side, I have 14 over 2 is 7. On the right side, I just have x. So allegedly, x is 7. So I've got the first part of my solution. X is 7. But Mr. X, wait. You just have one part of it. Where's the rest of it? So glad you asked. So glad you asked. I need to take that 7 that I found out, my alleged solution, unless I made a mistake, which is possible, and the whole video would be ruined. Let's try plugging it into the other equation and finding out what y is equal to. So y is equal to 4 times x, but I know what x is supposed to be now. It's supposed to be 7, so why would I write it? Why would I write x when I can just write 7? And then I get y is equal to 4 times 7 is 28 minus 10. So y is allegedly equal to 18. Man, I keep saying stuff like this, and I keep thinking that I might have messed up. I don't know yet. Kind of nervous. This is when I get nervous too. Everybody gets nervous when they're doing this stuff. It's very easy to make tiny mistakes. But let's try plugging it into both equations and seeing if it works. So let's see. in that first equation, let's try plugging it in. So y is equal to 18, allegedly. And then I get 2 times x, which is 7, plus 4. So 18 equals 14 plus 4. My goodness, 18 is equal to 18. Confirmed! Okay. Let's try it on the other one. This is where it gets kind of hairy. So y is allegedly equal to 18. And it's 4 times 7, because that's what my x is equal to, minus 10. 18 equals 4 times 7 is 28, minus 10 is 18 equals 18. Whew. Oh, sigh of relief, everybody. I can plug this in as my answer on my standardized test or my weekly checkpoint, or really, real life. It's better to do that in, actually going off and becoming a mathematician or a physicist or something like that. Those are awesome opportunities, and definitely curry favor with me, because I was a theoretical physics guy. But it definitely solved both of them. So let me go through and try to do this one as another example. But I want you to pause the video and you try it out first. I assume that you paused the video and you tried it out and you were happy with yourself, or think that you could improve and that you didn't just stare at the screen hoping for me to start talking again. So let's try it out. There's a lot of ways to solve each one of these. So in this case, they're both solved for y. This only works if they're both solved for a variable, the same value. And the solution, my x's will be the exact same for both of these equations, because it's supposed to be the same x and same y that solves both of them. And my y's are the exact same. So I should be able to substitute this right there. So I get 1/2 x plus 1 equals 3/2 x minus 1, allegedly. Well, actually, there's no allegedly. This is definitely written right. And some students like to say I'm setting them equal. Well, you've got to know why. You need to know why. That's very important. Let's find another color. Let's try this one. I haven't used green a lot yet. So I want to solve for x. So one way to do this is I can get it on the left side, or I can get it on the right side. But I notice I have more x's on the right side. Oh man, earlier I promised I'd show you both ways, but just remember that up here or over here when we had done this, when we had solved, if I'd taken it to the other side, I would have just ended up, my negatives would have canceled, but it's easier to make negative mistakes. But in this case right here, let's try it out. Okay, I want my x's on my right side again in this case because I have more x's over there. It's just easier. But maybe I didn't do that. Maybe instead, I took it over to the left side. So I have a 3/2 x on the right side. This is not the most efficient way, but it's the way we're going to do to show what would happen if you did it the other way, the less efficient way. So I'm going to subtract 3/2 x from both sides. I'm doing this to cancel this positive 3/2 x right here. There's nothing special about the fact that it has a fraction on it. I'm just subtracting that term from both sides just to kind of get rid of it. On the left side, I get 1/2 x minus 3/2 x. I'm just reordering so that you guys can see it a little bit more easily because I want to talk about this fraction jazz that's going on. And on the right side, I have 3/2 x minus 3/2 x is 0x. It's the same thing minus itself. So, and I'm just left with -1 over there. Now this part right here you might get a little bit nervous about. Don't. Notice these both have the exact same denominator. I have 1/2 of x minus 3/2 of x, so I'm left with -2/2 of x. So I'm really just subtracting or adding my numerators when they have the same denominator. Nothing's really changing. You can think of it as factoring in other ways, you know. Maybe you factor out this x. This might seem confusing, but it's just a reminder that factoring exists. Maybe you factored out the x out of both of them on the left side. And then you did that. You did your parentheses first, and you did 1/2 minus 3/2 is -2/2. Either way. But at the end of the day, you're going to get negative 2. That's not even close to what a 2 looks like. Negative 2 halves of x. Everything else is staying the same. Negative 2 over negative 2 over positive 2 is negative 1. So I have negative x plus 1 equals negative 1. That's just a little bit of the simplification stuff. And this one is a little bit hairier because I did come up with it on the spot and I wanted to talk about fractions. So now I just still don't have x by itself. So I want to get rid of this positive 1 right here. So I'm going to subtract 1 from both sides and be left with negative x equals negative 2. And you might think to yourself, oh, I'm done. I just have x by itself. No, you don't. No, you don't. You have a negative on that. You have a negative on that. So if you want to get rid of a negative 1, there's an invisible 1 right there. If you want to get rid of a negative 1, you need to either multiply by negative 1 to cancel the negatives, or you need to divide both sides by negative 1. I like doing the division part because it doesn't hide what we're doing, and students often pattern match that and mess that up on when it comes down to another number. So this negative 1 cancels with this negative 1. You're left with x equals negative 2 over negative 1 is positive 2. So this is where things get easy. Like, it might get scary because you're not sure if you made a mistake. But this is where things get easy because now I can just take this x equals 2 and plug it in and figure out what my y is. And if you did everything right up until here, it is correct. It's going to be correct. So I'm going to plug it into that, any of them, but I'm going to plug it into that top one for funsies. And I'm going to get 1/2 times positive 2, because that's what I allege that my x is equal to. So I get y is equal to 1/2 times 2 over 1, 2 over 2. So y equals 2 over 2 is 1, plus 1 is positive 2, because this is positive 1. So allegedly, my solution is 2, 2. Why is he wearing a tutu? But let's try plugging this into both of them and double checking that this is indeed the correct solution, because I could have made a mistake and you're just yelling at your screen right now, hey, Mr. X, stop. And I'm like, Mr. Noodle. So let's see. Let's try plugging this into the first one and seeing if, well, we know it works. We got it from the first one. So let's try plugging this into the second one and seeing if it works. So y is 2 there, equals 3/2 times x is 2 as well. So 2 equals, so there's an invisible 1 right here, as always. Top times top over bottom times bottom is how you do multiplying fractions. We get 6 over 2. 6 over 2 is 3. And 2 also equals 2. So it is a confirmed solution for both of them. In a future video, not exactly sure when I'm going to do it, I'm going to do something, different ways of doing it, because sometimes I'm going to do it multiple different ways. So in a future video, can't do it today though, I'm going to solve this system. And notice, you might say to yourself, well, that's easy. It's not quite as easy because they're not solved for y. I can't just automatically set them equal. And when I try to graph them, I could do it. Like, I'd have to get an x and find a y that goes with it, or get a y and find an x that goes with it, and, just graph each line individually. But in this case, it might not be a nice looking answer. So we're going to come up with other ways, something called elimination and something called substitution. And those are going to make it a little easier to solve any system of equations. Because when we do higher dimensionalities, when we do higher order systems, so 3 and 4 variables, even more equations. So you need 3 variables for 3 equations for a 3 variable system, and you need 4 equations for a 4 variable system, etc. We're always every part of our goal is to reduce it down further. Reduce it to a 3 variable system to a 2 variable system like this, and then reduce that to a 1 variable, and then find a solution. But it is going to be in a future video, and I'm not 100% sure when I have time for it, but I'm going to try to get it out to you.